Hi everyone, in this video we'll study merge sort. Now merge sort is a sorting algorithm which uses the divide and conquer paradigm to actually sort a bunch of numbers. Now here is the pseudocode for the merge sort algorithm. Now as it is a divide and conquer algorithm, what we have are the divide, conquer and combine steps. Now in the previous video, I explained what these steps are for a divide and conquer algorithm. So in the divide step, which is here, what we do is we divide the problem into smaller pieces or subproblems. Then we recursively solve these smaller subproblems. And how do we understand this is recursion? We are calling merge sort again. Okay. And then finally, in the merge step, we combine. So it's a divide and conquer algorithm where we divide a bunch of numbers over and over again, and then we recursively sort them, which is the conquer step, and then we combine. Now we'll understand the details of this algorithm slowly, but the most important part of this algorithm is the combine step, which is basically the merge algorithm itself. Now you can see that the divide is very simple. You just divide p plus r by 2. Now so far it's not clear what p is, what is r, what is a. We'll go over all of this. So let's first try to understand the merge step. Okay, so I have written the code for the merge down here. It is pretty big, but it's pretty simple. So let's first understand the merge algorithm. Now the merge is called multiple times when you divide the bunch of numbers. Now say you have a lot of numbers. So I'm going to pick this red black color and let's assume that this is step 1. Okay. So first we have a whole bunch of numbers. Okay. And we are constantly dividing them into small groups of numbers, and then we are combining them in the merge step. So let's consider 8 numbers. So 2, 4, 5, 7, 1, 2, 3, 6. Okay, so there can be many numbers that you need to sort, but when a particular merge is called, you have these 8 numbers because you're constantly dividing these large set of numbers that you want to sort into smaller groups. So this is the array. What I've shown is this array A where all these numbers are stored, and this is the small portion that you're interested in. Now in this array, let's just assume that these are the indices of these numbers. Now in the pseudocode, I'll assume that the array starts from 1. Now depending on the language that you use for programming, your array could start from 0, but here we just assume that the array starts from 1. Now you're looking at this portion of this array between 9 and 16. Okay, so this is what is called when you call merge and you pass a to it, and you have essentially what you've passed is 9, 12 and 16. So what is 9? So your p is 9, your q, we'll get to that in a moment, is 12 actually, and your r is 16. So p is the initial of this array, q is the end of r is the end of this segment, and q is the center point. Now if you go back here, we will see that this is where q is defined, p plus r by 2 in merge sort. Okay, so you basically divide it, call merge sort, and then there is this merge which you combine the results. So let's look at this merge a little more carefully. Now what we are first going to do is we are in this merge, we are first going to define n1 and n2. Okay, so and we are going to create 2 arrays L and R. Okay. Now, and in this we are basically going to store the left and right sides. Now, to understand this a little more carefully, let's look at left. Now, left is essentially the 2, 4, 5, and 7. Okay. And the right is 1, 2, 3, and 6. Now, you will notice that the left and the right are sorted. And why is that? Now let's go back to merge sort. So merge sort first divides the array, and then, so in this case, let's assume that you take this array here that we are considering, the A. Now merge sort is going to divide it into two pieces, each of size 4. Now, the first time when you call merge sort here, it will sort the left side of the array. And then when you call merge sort here, it will sort the right side of this array. That is why the left and the right are now essentially going to be sorted. Okay. Now, if you look at the merge step here, what we did was this. What we have is we've defined n1 and n2. So if you just look at n1 is 12 minus 9 plus 1 equals 4. That is why we have n1 equals 4, and that is the size of the left. Now n2 is r minus q, which is 4. So essentially, we are looking at the left side and the right side, which have been sorted recursively. Okay. Now, the left side has been sorted by merge sort, the right has been sorted by merge sort, and the goal is to combine them to create a sorted array. Okay. So, in the first two steps of merge, here and here, we've created n1 and n2, and then we copy over these arrays in lines 4 to 7 into L and R. So you have the array in place, which has half of like this entire array A. Between 9 and 12, everything is sorted. Between 13 and 16, everything is sorted. And you just copy them over to L and R. Okay. Now, what are we going to do? In step 2, we are going to look at 8 lines, 8 and 9. So what we are going to do is, we are going to increase the size of L and R, because they both, not increase, put the last element to be infinity. That will be useful for some comparison. So at this point, I've not still explained the algorithm. I'm just laying the foundation, and then we will explain the algorithm so it becomes easy for you to understand what's happening here. So let's once again draw A. So this is your A. And what we're going to do is, we are essentially going to do this. 2, 4, 5, and 7. Then the last number is infinity. Then right, it's 1, 2, 3, 6. And you're going to add 1. It's infinity. Okay. And sorry, this should be left. I and j initially will be kept to 1. So we're going to put I and j here as well. Okay. So they are both 1 here. And now, so I'm going to just add infinities here as well. Okay. So that is what we have done in these steps. Okay. Now, essentially, we're going to look at merge sort here. So now, how does merge sort work? Now, merge sort, you can consider the left and the right as two sorted decks of cards, and you want to sort both of them together. So what you do is, you look at the first card from both the decks. Now you compare them. Now, depending on which direction you want to sort, ascending or descending, what you do is you take, say, the smaller card and keep it aside. Okay, so say the left is smaller, you keep it. If that's how you want to sort it, then you pick the next card from the left. Do this comparison again. So basically, whichever is the least among the two comparisons, you are going to put them on a third deck. Okay, and that is essentially how we are going to create this completely sorted array. Now, how would this help? So this is a recursive algorithm. So if you go back, you're going to take a big array in merge sort, which is your A here, and then you're going to divide it up first into two smaller pieces. Those two smaller pieces basically you'll call merge sort recursively, so they will keep getting divided. And then when you get to this merge, when you have, the way to think of it is, say at this point, once you have taken a big array A, merge sort in line 3 and my line 4, it's going to sort those two smaller arrays. And then in line 5, what you're going to do is you're going to merge these two. So you have two sorted arrays, and you're going to merge them to get a bigger array. Okay? And what we are studying now is how to get this. Okay? And later we'll see how all this combines and understand the working of merge sort as well. Okay? So let's go back to what we were doing. So till line 11, we'll have basically ing here. Now let's focus on the algorithm from lines 12 to 17. Let's see what we are doing here. So what we have here is we are initially starting from k equals p. So if we go to step 1, we can maybe just, for sake of completion, we can put k here. So k is starting from p. Okay. And in step 2, we are now going to iterate. Okay. So first, k is going to increase. So k will come here. Okay. So I'm just going to put all these indices one more time so that it's easy for us to understand. So k comes here. You have your I. Okay. Now what you are doing is you are comparing the left and the right. Now let's see the right. The right's first element is 1 and the left's first element is 2. Okay. So if left in lines 13 to 15, what you have is if left is less than equal to right, you are going to take the left and place that in AK. Otherwise, you're going to do that for the right element. Okay. So in this case, when you have step 2 like that, what is going to happen is I'm going to erase something and put a new. So I'm going to make this in blue. So this is 1 is lower. So what you're going to do is you're going to take this 1, copy that over to the original array A in position 9. So this 2 will be overwritten to 1. Okay. And then J will move forward here. This is how it will look like at the end of step 2. Okay. So you will copy this over. This line will execute. So I'll copy that over. Then you'll increment J to J plus 1. Let me erase these things. Now let's look at step 3. In step 3, we'll once again copy this entire array over. So 9, 10, 11, 12, 13, 14, 15, 16. So I'm just going to use blue to write 1 here. And we will have 5 7, 1, 2, 3, and 6. I've just left out the element in index 10. We'll see why that is the case. So let's just write L and R as well. So L has 2, 4, 5, and 7, and infinity. That is your L. Your I was here. Your R is this, and your j was here. Now at this point, your k in step 2 was, at the end of step 2 was here. So you're now going to compare. So you're going to compare 2 and 2. So it's going to go here, and you can see that that's for less than equal to. So this 2 in left is going to get copied over to this 10. And that's what is going to happen. It's going to overwrite the 4 that was there from step 2, and this is what is going to happen. And what we will do is, we will rewrite that in red and move the I here. Okay, so that's where I will move. And where will be k? K will be here. That's what is going to happen at the end of step 3. I hope you're understanding how this process is happening. So k is slowly moving forward. Now let's go to step 4. Okay, so in step 4, the same thing is going to repeat. This is, we're going to look at A. So this is the entire A again. So 9, 10, 11, 12, 13. So these are the indices one more time. It's important to understand merge sort in this way because otherwise it can get a little bit more confusing. So once again, I'll use 1 and 2 here, and then there'll be 5. I'm just going to write it, and we'll rewrite it in a second. So this is the state of the array, right? Now, what happens is you're going to compare 4 and 2. 2 is less, so it'll be copied over in place of this 5. So you're going to have 2 copied over here. And your left will have this feeling. That is, it will have 4, 5, 7 and infinity. I'm just going to put 2. Because in that comparison, 4 was compared with 2. 4 is greater than 2, so nothing is going to change. So your left will look exactly like it did before this step. Now for right, j will move forward. So for right, 3, 6, infinity, j will be here, and then you will have 1 and 2 in blue. So I'm just highlighting everything in blue here. Now we'll repeat this process one more time for step 5. So let's do that. I hope it's clear at this point where we are going with this. So the algorithm has moved up, but I hope you can understand what we're trying to do here. So in step 5, we will now compare. Essentially, we'll be comparing this 4 with this 3, and 3 will get copied over. Okay, so I'll draw this. 5, 6, 7, 8. These are the indices. It's a good idea to write the indices as well, because then you know exactly how the code is working. And we will have 1, 2, 2, 3. The 3, this 3 which is getting copied over. And the rest will be 1, 2, 6. And here, k will be here. Now, your L will not change. Your L will have 2, followed by 4, 5, 7, and infinity, with I being here. For your R, your J will move forward. Just so we'll have 1, 2, and 3, because we're writing in blue to show the elements that have been already been explored. Okay, this is the state after step 5. Now repeating this approach for step, we do for step 6, this is what is going to happen. So we can do step 6. Once again, we copy over that array, A here. So we have A and 1, 2, 3, 4, 5. So this is exactly how it's going to look. I hope it's becoming clear at this point how this algorithm works. So we are going to compare 4 and 6. 4 is smaller than 6, so 4 will get copied over. So we'll have 1, 2, 2, 3, 4, and these elements are yet to be explored, which are, and our k will be here at this point. Okay, and the way L will look is like this. So L will have 1 and 4, which have been copied over, and I will be here 5 and 7. And for R, J will be stuck at 6, and 1, 2, and 3. Okay. And if we repeat this process, finally we will get the sorted array. I'm not going to repeat all the remainder of the steps. I hope it is clear what we have done. So we will have 9 such steps. And at the end of the 9th step, I'm just going to do ... here so that it's clear. And at step 9, this is how it will look, which is at the very end. 1, 2, 3, 4. So these are the indices once again. And all of them will have been sorted. So we'll have 1, 2, 2, 3, 4, 5, 6, and 7. So that this time and k will be here at this stage. Then the left will look like this. We would have copied everything over. So we will have infinity here. I will be stuck here. Similarly, J will be here. Now you will have an understanding of why we put the infinities. The infinities were just to help our comparisons. That's the main reason why those infinities were added in the first place. So this is how our left and right will look. So at this stage, what we have done is we have managed to sort the entire array A in place itself. So this is what the merge algorithm would do. It will basically sort A in place. So remember that this algorithm here, first it makes these local copies of left and right in these places here, but it sorts A in place because at the end when merge will complete, the memories for left and right will be released. Okay, it's a recursive algorithm, so you cannot allocate memory and not release it. But because merge portion is not the recursive parts, you can allocate memory in left and right, and at the end of this, when you get to the end of merge, this temporary memory for left and right will be released, and you will have A being sorted in its place. Now, let's go back to merge. If you go back to merge, what we have is it's a combined part of merge sort. So in the merge sort, you're dividing the big array into smaller pieces, and you're going and you're calling them recursively over and over again in the conquer steps here. That's what you're doing. And finally, when you have conquered 2 arrays, you will have 2 subarrays that are sorted, and in the merge we combine them. So let's see how merge sort actually works. So we just looked at the merge, now we'll look at merge sort. So now let's consider that your A has these 8 elements. Okay. So what merge sort would do is, it would first divide it up into 2 smaller arrays. So if you have A like this, 5, 2, 4, 7, 1, 3, 2, 6, it is first going to divide it up into 2 pieces. Okay, and this is a pictorial representation, so just to help you understand, it's going to happen recursively. So it's going to first divide it up into 5, 2, 4, 7. That's when the merge sort is going to get called, which will then break this up to 5 and 2. This 4, 7 will get broken up into 4, 7. And the same thing will happen here. So it will be 1, 3, 2, and 6. You'll get these things broken up like this. This will be broken up into 1 and 3. And this 2 and 6 will be broken up into 2 and 6. So you're continuously recursively breaking them. And then this will break up to 5 and 2. And this will be broken up into 4 and 7. Now when you get to the stage that you only have a single element, there is nothing to sort. Okay, so at that point in merge sort, you'll start merging. So you're just going to break the entire array recursively into smaller and smaller pieces. Okay. After this, you're basically, the merge will kick in and you will start merging everything. Okay. So how do we know that this is where the merge algorithm will stop? If you go back to the merge algorithm, see the first line right here. This takes care of that you keep dividing till that point. At this stage, we've divided everything. Now everything basically will be merged in the combine step, and this is what is going to happen. So 5 and 2, they will get combined to produce 2, 5. 4 and 7 will get combined to produce a sorted array 4, 7. 1 and 3 will get combined to produce the sorted array 1, 3. And 2 and 6 will get combined to produce a sorted array 2, 6. These will then be combined to produce 2, 4, 5, and 7. Similarly here, these will be combined to produce 1, 2, 3, 6, which then be combined by merge to produce the final sorted array, which is 1, 2, 2, 3, 4, 5, 6, 7. Okay, so this is how merge sort will work. It will keep continuously dividing, and once you've divided everything, it will combine everything to give you your sorted array. Okay, so we looked at merge sort, we looked at merge, and we'll conclude this video by doing some simple runtime analysis. So runtime analysis or merge sort is pretty simple. It follows the same logic as any divide and conquer approach. So first, we have the divide step. The divide is very easy. We just divide the array. Okay, so that's dn. That takes theta of 1 time. Now the conquer, you're going to take an array of size n and divide it into two arrays of size n over 2. So it's essentially 2n divided by 2. So if you assume that your runtime for an array of size n is tn, in the conquer step you will get 2tn by 2. The combine is where most of the magic happens. Now what you're doing in combine is you're comparing the elements. Okay, you're doing n comparisons at most. Okay, so there are n comparisons in the worst case, and therefore you will have the time for combined step Cn as theta of n. For we can write Tn equals theta of 1 if n equals 1, and 2Tn by 2 plus theta n if n is greater than 1. Okay, now this, if you solve this, it is going to give you n log n time. Okay, so this once solved will give us n theta of n log n time, And we'll look in a second how we can get this. I'm just telling you that this will get solved to give us a runtime of theta n log n. Now, this is the best runtime for any sorting algorithm. So you cannot have a sorting algorithm run more efficiently asymptotically than this. Okay, so merge sort is one of the sorting algorithms which can achieve n log n, and that's the best that you can do. So we'll just talk about how we get n log n here. So if you look at Tn, and let's just pull this back here, what you're having is 2Tn by 2 plus theta n. So essentially theta n can be written as Cn. So that'll be Cn, and you're going to get Tn by 2 here and Tn by 2 here. So you initially have Tn that gets split in this way. Then each of those Tn by 2 will then get split over. So you're going to get Cn. And if you're going to split this, this is going to be Cn by 2 because the input size is not n but n by 2. And then you're going to have, it's not an arrow here. Then you'll have Tn by 4 and then Tn by 4. And the same on this side. So you're going to have this kind of tree developing here for merge sort. So essentially this Tn is your step A, this is your step B, and this one is your step C. Now, if you keep doing this, ultimately this is what you will get. You'll have Cn, which gets run by Cn by 2 and Cn by 2, which then gives you Cn by 4, Cn by 4, Cn by 4, and Cn by 4. So every time your input size is getting divided by 2. So how many times can it get divided? It can only get divided log n times because your input is size n. So you keep dividing that by 2, you will get log n. So at the very end, you will get C, 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 and you will have n of these here. So you can see that at every step, if I pull arrow, this is Cn. For this line, it's Cn plus 2 plus Cn plus 2, which is again Cn. For this, it's going to be Cn. And at the very bottom, you're going to have Cn. And the number of such levels is going to be log n. Therefore, your height is equal to log n, and you will get the runtime, therefore, to be Cn, basically, instead of writing, we take your runtime will essentially be Cn multiplied by log n, just nothing but theta of n log n. So we just showed that the runtime of merge sort is n log n. So what did we study? We studied the merge sort algorithm. We looked at the algorithm and we understood that how we can apply divide and conquer. We looked at the conquer step first, which is basically the merge. And then we saw how by doing this merging, we will get the array to be sorted. So if you want to remember merge sort in one slide or just visually, this is the picture that you should remember. Then we looked at the runtime analysis of merge sort, and we showed that the runtime is theta n log n. With this, I'll conclude this video. Thank you for watching.